Hello there, welcome to another tutorial. This one's going to be a fairly brief tutorial showing you how you can use complex numbers to derive some of the trigonometric identities that you will have seen in your formula books and textbooks at school, but that maybe no one explained before where they came from. So I'm going to start off by recapping some things about complex numbers that we're going to find useful, and then I'm going to show you how easy it is to derive some of these trig identities. So the first thing I want to do is to remind you what a complex number looks like. So a complex number is a quantity z which we can write in the following form as a plus ib. And the thing which distinguishes a complex number from a real number is that the factor I there is the square root of -1. So any place in which we see I squared, we can replace it by the real quantity -1. Okay, so that's one way in which we can write down complex numbers, and that way is often called the Cartesian representation of a complex number. That's as these two distinct parts called the real and imaginary parts, A and B. But there is an alternative way of writing down the same complex number, and that's in this form: z equals re to the I theta. This is called the polar representation. And these two representations are connected together by a graphical representation for complex numbers as points on a two-dimensional plane. So I can represent the complex number z by showing the point on the plane located at coordinates a and b in Cartesian coordinates. So that's one way of representing the complex number z. And these two representations are connected together because if I were to represent this in polar coordinates, where r is the length of the distance from the origin to z, so the length of the hypotenuse of a right-angled triangle there, and theta is the angle measured from the x-axis. So that's an alternative representation. So let's just briefly confirm how the Cartesian and polar coordinates are connected. So if we want to convert from Cartesian to polar coordinates, then we need to know r, which is the length of this hypotenuse. Well, we know from Pythagoras that r squared must be a squared plus b squared, and the reason we're allowed to do that is that we have a right-angled triangle if we've got a and b as our Cartesian coordinates. What about the angle theta? Well, if you check your basic trigonometry, you'll find that tan theta is b over a. So that's a way of converting in one direction. Of course, we could square root here to get r, and we could take the inverse tan to get theta. What about converting the other way? Well, again, from your basic trigonometry, you'll find that a is r cos theta and b is r sine theta. Okay. Now, taken together with the polar representation, this means that we can equally well write z as r cos theta plus I sine theta. Okay, so that's just a reminder of some basic facts about complex numbers. The next ingredient I'm going to need in deducing my trig identities is to remind you of some basic algebra to do with indices, that is powers. So let's remember some basic algebra to do with powers. So the first thing I want to recap is what happens if we multiply two different powers together of the same quantity. So x to the n times x to the m, where n and m are different numbers. Remember that in this situation we simply add the powers together. The second thing that we want to recap is the case where we raise a power to another power, so x to the n to the m, and in this case we multiply the powers. A third example that we need is where we take a product of quantities, say x and y, and we raise that product to a power. In that case, that's the same as raising both of the factors to the same power. So remember these identities. I'm going to label these A, B and C because we're going to use them in a minute. Okay, they're the basic ingredients that we need to deduce some of the trig identities that you will have seen in the formula books. So now that we have our basic ingredients, let's put them together and see if we can deduce something cool. So I'm going to start off here by supposing that we've got a general complex number z. So remember that z can be written down in the polar form as re to the I theta, which if we wanted in more detail is r cos theta plus I sine theta. There are two different ways of writing down the exact same number. Now what's interesting here is to consider z squared. Now in order to square z we could use either of these two forms, and doing that we will get two different looking expressions, but they must both be equal, and this is the trick that enables us to deduce a trig identity. So let's consider z squared. I'm going to label the first representation 1 and the second one 2. So from equation 1, z squared is, well, in representation 1, z is re to the I theta, so z squared must be re to the I theta all squared. Well, now remember our identities that we got earlier. Over here, if we have a product of quantities raised to a single power, we raise both quantities in turn to that power. So let's do that here. It must be that the result here is r squared multiplied by e to the I theta all squared. Okay, but now look at this second part. We have a power to another power. So again, recall our basic rule of algebra, rule B, one power to another, we multiply the powers together. So let's do that here for our complex number expression. So applying that to the second part, we must get e to the I2 theta. So what does this tell us? Well, this tells us that if we square a complex number z, that we square its modulus, that is the length of that hypotenuse from the origin, and we double the angle measured from the x-axis, because we've got 2 theta here instead of just theta. Okay, well finally let's just write out what we get here, converting into the full polar representation with cosine and sine. So here then we must have cos of 2 theta plus I sine of 2 theta. So we deduce that expression for z squared by using this form number 1. But now let's do the same thing using expression number 2 for z and see what we get for z squared. So I'm going to do that over here, and we'll note that from expression 2, z squared must be all of this expression here squared. So we've got to be careful with brackets here, make sure we bracket this correctly. But now what do we have here? We have a product of two quantities raised to a single power. So again, we can express this as the product of the two powers using our basic rule of algebra that I wrote on the previous page. Okay, well we can't do very much with r here, but we could multiply out this bracket. So this is of the form x plus y, and we're squaring it, so we could multiply out the bracket. So the first thing we'll get is cos theta multiplied by itself, which we write in the shorthand notation cos squared theta. That's from the first term times itself. Then we will have two cross terms from multiplying out, so we will get 2 lots of I sine theta cos theta. Finally, we'll get the last part squared. Now be careful here. We've got I sine theta all squared, which is the same as I squared sine theta squared. And remember, the crucial thing about complex numbers is that I squared is minus 1. So actually here we get minus sine squared theta. Okay, so the point here is that we've now got two different expressions for the same quantity, z squared. I'm just going to write this one out again, collecting together the real and imaginary parts in this. So it's collecting together the real part gives me cos squared theta minus sine squared theta, and that leaves us with the imaginary part 2i sine theta cos theta. So we've deduced two different expressions here for z squared, which means that these two expressions must be equal. So let's put these equal to each other, and the first thing you'll notice that we can do is to cancel the r squared on both sides, which leaves us with the trig parts being equal. And this is how we deduce our trig identities. So I've left the two expressions here at the top. So what have we deduced? We've deduced that cos of 2 theta plus I sine 2 theta is the same thing as cos squared theta minus sine squared theta plus I lots of 2 sine theta cos theta. Okay, well this doesn't appear very useful so far, but there's one crucial thing that we need to remember. So we need to remember that equality of complex numbers means equality of both the real and imaginary parts. So let's look at this. Equality of complex numbers: if one complex number written as a plus ib is equal to another written as c plus id, where a, b, c and d are all real numbers and the i's here are the only imaginary units present, then the only way these two numbers can be equal is if the real parts are equal and their imaginary parts are equal. In other words, a must equal c and b must be equal to d. So applying that to the expression that we deduced above, the real part on the left hand side, which is cos 2 theta, must be equal to the real part on the right. And we've deduced our first trigonometric identity, which is commonly found in formula books, which states that cos 2 theta is cos squared theta minus sine squared theta. What about the second identity? Well, we can get that by equating the imaginary parts. The imaginary part on the left and the imaginary part on the right. These must be equal, which tells us that sine of 2 theta is 2 sine theta cos theta. So just by using basics of the representation of complex numbers in Cartesian versus polar form, and by using the basic rules of algebra, we've derived here what are often called the double angle formulae. Okay, so I'm going to finish for now and leave you with a challenge. By the way, this same trick can be used to derive all kinds of different identities between trigonometric functions. So I'm going to leave you with an exercise here, which is to do the same for z cubed and see what you get. And obviously you could even go to higher powers, z to the power 4 and so on. So that's one exercise. The second one that you might want to think about is, could we, by a similar method, gain a formula for the cosine of a sum of angles, or the sine of a sum of angles? So that's another one to think about as well, which uses a very similar trick. Okay then, thanks very much for watching, and enjoy complex numbers.